Hi folks, today we are going to explore an LCD driver, or more accurately, a driver together with its expansion companion. The devices we are looking at are the PCF8578 and the PCF8579. The PCF8578 can operate in standalone mode. In this configuration, the column outputs C32 through C39, and the row outputs R0 through R7 are fixed. In other words, R0 through R7 always function as row drivers, while C32 through C39 always function as column drivers. The remaining pins are much more flexible. They can be configured as either rows or columns in groups of 8, depending on the multiplexing mode that is selected. For a 1:8 multiplex ratio, the row outputs are R0 through R7. For 1:16 multiplexing, they become R0 through R15 or C15. For 1:24 multiplexing, the rows extend from R0 through R23 or C23, and finally, with 1:32 multiplexing, the row outputs extend from R0 through R31 or C31. One of the greatest strengths of this family of drivers is its expandability. A single PCF8578 can be expanded with up to 31 PCF8579 devices, allowing control of as many as 40,960 display dots. The PCF8578 contains an internal static RAM organized as 32 by 40 bits, where all display data is stored. This memory is divided into 4 banks, each containing 40 bytes. Altogether, that gives us 1,280 bits of storage. Whenever the display memory is accessed, data is transferred through the I2C bus. The first 8 data columns, numbered 0 through 7, cannot be displayed. Instead, they are available as general-purpose storage, and also provide compatibility with the PCF8579. Another useful detail is that there is a direct relationship between the X memory address and the physical output column. The demonstration panel used in this project contains 1 PCF8578 and 3 PCF8579 expansion devices. Communication is handled entirely through the I2C bus. On this particular panel, the SA0 pin is connected to VSS. This gives the device a 7-bit I2C address of 0111100, or in hexadecimal, 0x3c. If the SA0 pin is instead connected I, the address becomes 0111101 or 0x3d. So you can think of the SA0 pin as selecting the final bit of the I2C address. Fortunately, both datasheets include several practical implementation examples, which are extremely helpful. Unfortunately, the programming documentation itself is not always as clear as it could be, and it can sometimes lead to confusion. This driver family is remarkably flexible, allowing an enormous number of configuration options. Naturally, that flexibility also makes it more challenging to understand and use. In many cases, only the most determined designers take full advantage of its capabilities. A clearer programming guide would certainly encourage wider adoption, and that is exactly what we will try to contribute with this project. We will begin by looking at the standalone configuration, where the PCF8578 is configured in mixed mode. This mode supports several display arrangements, 1 to 8 multiplexing, with 8 rows and 32 columns, 1 to 16 multiplexing, with 16 rows and 24 columns, 1 to 24 multiplexing, with 24 rows and 16 columns, and 1 to 32 multiplexing, with 32 rows and 8 columns. The easiest way to understand these configurations is simply to look at the table in the datasheet. Keep in mind that every PCF8578 and every PCF8579 is addressed through the I2C bus. By changing the SA0 pin, we gain access to a second address range. This effectively doubles the number of expansion devices, allowing one PCF8578 to operate together with as many as 31 PCF8579 drivers. Communication is handled through 5 different commands. These commands allow us to configure features such as the subaddress, the RAM bank, the mixed mode, and several other operating parameters. One bit deserves special attention, the C bit. When the C bit is set to 1, it tells the driver that another command byte will follow. When it is cleared to 0, the driver knows that every following byte is displayed data, which will be written directly into the LCD memory. Access to each PCF8579 expansion driver is determined by its subaddress. This subaddress is selected through the pins A0 through A3. The internal RAM can operate in 3 different display modes: character mode, half graphic mode, and full graphic mode. A 4th combination exists, but it is reserved and must not be used. The hardware configuration chosen at the beginning of a project directly determines which display mode can actually be used. In our case, this panel operates in character mode. To support the reverse engineering process, I developed several small software tools to make the job much easier. The first step was to use the set mode command and modify bits 2 and 3 to enable the built-in blinking function of the LCD. Next, I implemented a second blinking routine. Instead of using the hardware blink feature, this version simply inverts every segment under software control. This allowed me to verify the total number of controllable bits available on the hardware. Once that was working, the next step was to illuminate the display, one column at a time. Since every column contains 7 segments, it quickly became clear that we were dealing with a character configuration, most likely based on a classic 5x7 character matrix. Of course, the display itself does not follow a perfectly regular layout. Instead of having, for example, 12 identical 5x7 characters, it combines character groups of different sizes, together with several predefined symbols on the right-hand side of the display. To make room for these symbols, some character cells are narrower, and the column mapping also changes from one section to another. After running the column scanning script, a clear 5x7 character pattern becomes visible between column 43 and column 78. One interesting observation is that although the driver accepts data for column 48, which would normally be the 6th column, it actually uses that position as the spacing column between adjacent characters. With these observations, it becomes possible to display text messages on the LCD. Because several different scripts were created during the reverse engineering process, I will also make all of these example programs available with this video, so you can use them while testing your own hardware. There is one important limitation worth mentioning. The Arduino wire library is limited to 32 bytes per transfer. For larger updates, you will need to split the transmission into multiple I2C transactions. Finally, let's look at the wiring required to bring this panel to life. First, connect the logic supply to positive 5 volts DC. Next, connect the I2C bus using the STA and SCL signals. Each of these lines should have its own 1 kΩ pull-up resistor. Finally, provide a negative supply of approximately -4 volts DC. The datasheet clearly explains why this negative voltage is required, and even provides the information needed to calculate the exact value. For this proof of concept, however, -4 volts DC works perfectly. You can even add a potentiometer to adjust the display contrast and obtain the best visual result. Once you have followed these steps, you will have everything needed to bring your own panel to life, whether it uses a single driver or a complete chain of expansion devices.